It's my great pleasure to introduce Professor Nicolás Yunes. He's a quite well-known physicist in the field of general relativity and even beyond general relativity, and in particular in the extremely strong field gravity regime. And today he is going to tell us about probing strong gravity when gravity waves. Should start? Or not. Hello. Is that okay? Better. Okay. Okay, so thank you very much for the invitation to Japan and the invitation to speak in this symposium. It's always a pleasure to be here and to interact with you all. I always learn something new. So today I'm giving more of a colloquium style talk on what we can learn about fundamental physics. What have we begun to learn with gravitational waves emitted in the merger of binary neutron stars? So some of you already know that I am the director of this new center for physics at the University of Illinois in Champaign, which excuse me, there's a message from Zoom that needed to get fixed. Yeah, so I work at the University of Illinois in Urbana-Champaign, which looks like this, but in reality it looks like this. And I lead a group of researchers in a variety of fields. I'm going to be talking today about work done by a majority of the group here. In general, my work has sort of rotated between experimental relativity, so tests of GR that we can do with solar system observations or binary pulsar observations of gravitational waves, as well as more theoretical work on understanding gravitational theory and black hole solutions, and how can we connect those observations to nuclear physics and to particle physics. So today, I'm going to focus on what I'm going to call fundamental physics that we can learn with gravitational waves. So I'm going to define what I mean by fundamental physics in a second. Now, before I go on and define that, let me just tell you a little bit more about the sources that we are detecting with gravitational waves. I'm sure you've seen this animation before. It was created by the LIGO collaboration, and it shows a numerical relativity simulation of two black holes of roughly 30 times the mass of our sun, slowly spiraling into each other, and eventually colliding at about half the speed of light and producing a burst of gravitational radiation, of gravitational waves, that then travels at the speed of light, pretty much unimpeded by anything between the source and us, until eventually, there we go, it reaches Earth. And the effect of a wave when it goes through matter is to distort the relative separation, obviously not drawn to scale here. Fortunately, at the time when these waves were going through, there was an experiment in Hanford and in Livingston, an interferometric experiment trying to observe gravitational waves, trying to measure an interference pattern as the wave goes through. That's what the wave does. It sort of changes the proper time of propagation between photons that are emitted or that leave from this beam splitter in the center and head out to one of the mirrors over here and another one of the mirrors over here, which are separated by roughly 4 kilometers. And then the light recombines at this beam splitter, and the interference pattern, if any, is observed at the photodetector. Now, if a wave goes through, then that time of propagation changes, which then induces an interference pattern, which we can then detect. And then through data analysis, you can try to infer the source that caused that interference pattern. And it's essentially a gravitational wave in a nutshell. Okay. And of course, that happened in 2015. And it was very exciting, and some people got the Nobel Prize. You all know this. But what also happened about 2 years later was the observation of a different type of gravitational wave, gravitational waves generated by the merger of two neutron stars instead of two black holes. Okay, and so what I'm going to show you now is what's called a spectrogram. So over here, I'm going to plot the frequency of the data as a function of the time. So a frequency time plot, and I'm going to show you the power in the signal over here. And I'm going to also sonify those gravitational waves so you can hear the gravitational waves as they are going through the detector, okay? On the top, you will see counts of photons detected by the Fermi detector, this Fermi satellite on Earth at the same time. Okay, so here we go. Hopefully this will work. We tested it for like a solid 30 minutes before the talk started. Okay, so the first were the gravitational waves, the sound of gravitational waves, and the other one was the sound of photons. Of course, photons don't make a sound, but you know, I like to show that particular plot. And what's notable here is that this peak of this photon count peak that was observed by Fermi occurred very close after the peak of the gravitational wave emission, about 1.7 seconds afterward. And so we had an event, an astrophysical event, that we know generated these gravitational waves and these photons. And because these are different messengers, there's photons versus gravitons, we could compare their time of arrivals, and therefore, assuming light travels at the speed of light, we could then place a relative measurement on the speed of gravitational propagations, which was found to be equal to the speed of light to 1 part in 10 to the 15. And of course, those are not the only events that have been observed since LIGO turned on. Also, and Virgo turned on in Italy, and then shortly thereafter, Kagra here in Japan. About 100 events have been observed with a variety of morphologies and durations produced by a variety of systems, including black hole binaries, neutron star binaries, and black hole neutron star binaries. Here is what's called a stellar graveyard, which essentially shows all of the sources of gravitational waves that have been observed. So the way to read this diagram is that here on the y-axis, you see solar masses, and then you see blue dots, right? And so, for example, over here, this blue dot, it corresponds to an object with roughly 7 solar masses, which combined with an object of roughly 11 solar masses to produce an object of roughly 18 solar masses, all as inferred from the gravitational waves detected by that event, or from that event. The x-axis means absolutely nothing. It's just a way to arrange it so that it looks pretty. And then the yellow points here correspond to neutron stars that have been observed electromagnetically, whereas the red point here corresponds to black holes that have been observed electromagnetically. Okay, and so this gives you a sense of the black holes that have been detected by LIGO Virgo Kagra so far. And so there's this network soon in the future. We hope that LIGO India will join the network, and there's already plans to continue pushing gravitational wave observation into the next generation era through, for example, Cosmic Explorer or Einstein Telescope in the US and Europe, as well as detectors perhaps in China. And of course, space-based detectors, both LISA, which is a NASA ESA mission, as well as possibly SIGO in the future and other Chinese missions. And so very clearly, the future is very loud in gravitational waves. We are currently here in the 2024 part of this diagram, observing with LIGO, Virgo, and Kagra different capabilities. And these detections will continue during the 4th observing run, of course, that's happening now, as well as in the 5th observing run, which will start in a few years. And so more and more data is going to be collected. Hundreds of events are going to be observed. And so the question is, what are you going to do with that data? What can we learn from that? That data is going to get collected, whether we like it or not. And so it would be a missed opportunity to not try to extract the most science from it and try to see what we can learn about different aspects of physics. So the rest of this talk is going to be organized as follows. I'm going to give you a brief introduction to what gravitational waves are, because I was told that this is going to be an audience going to be mixed with, of course, gravitational physicists that I can recognize here from the conference we just had, the JGRG meeting, but also particle physicists and condensed matter physicists. So I'll remind you of what gravitational waves are as we move toward understanding how those waves can teach us about fundamental physics and about what we can learn in the future, or how perhaps we can use new techniques to extract information from gravitational waves in the future. Okay. So if you all are experts in relativity, I ask for your forgiveness. I am going to present some of the basic stuff on what gravitational waves are. So very briefly, I'm going to define the extreme gravity regime as that where gravitational interaction is simultaneously strong and dynamical. During the observation time, gravity is changing, and we can measure that change rapidly. Gravitational waves then are to be understood as wave-like perturbations in the gravitational field, far away from the source that emitted them. And according to Einstein's theory of general relativity, they are generated due to accelerating masses, for example, accelerating sources due to temporal variations in the multipolar structure of the space-time. Here is a movie that shows two black holes going around each other and producing these oscillations in the space-time metric in the gravitational field, which we then detect very far away from the source with our detectors on Earth. Now, these gravitational waves propagate according to relativity at the speed of light, and they decay with a 1 over r fall off. And of course, the spectrum of gravitational waves is varied because the frequency of the gravitational wave is intimately tied to the orbital frequency of the source that emitted the gravitational waves. And so essentially follows Kepler's third law. Very schematically, the frequency of the gravitational wave scales as the mass of the system divided by the orbital separation, or the characteristic orbital separation of the system cubed to the 1/2. And so if the objects merge, if they touch, the orbital separation is roughly the size of their horizon. Size of the horizon in relativity is proportional to their mass. So of the 3 powers of mass here, 1 cancels, leaving a 1 over m squared. Take the square root, it roughly scales with 1 over mass. What that means is that gravitational waves emitted by low mass mergers are going to be of high frequency, whereas gravitational waves emitted by very massive objects are going to be of very low frequency. This is what LIGO and ground-based detectors are detecting gravitational waves in the hundreds of hertz, whereas if you want to detect, and those are generated by mergers of neutron stars and stellar mass black holes. But if you want to detect the gravitational waves emitted by colliding supermassive black holes, or a small black hole falling into a supermassive black hole, then you need to go to much lower frequencies. And for that, you require these space detectors. Okay. Of course, if you want to detect gravitational waves of even lower frequencies, you have to use pulsar timing arrays or perhaps cosmological observations. But I am not going to be discussing those in this talk. Now, how do we extract information about nature from these gravitational waves? So what I'm showing you here is the strain sensitivity as a function of frequency for different science runs that were carried out before advanced LIGO was online. So this is back when I was a grad student, okay? And so what you can see here are different lines, which are different science runs carried out with instruments of enhanced, with ever better sensitivity. So this one had some sensitivity, but then the instrument was improved and the sensitivity moved to this green line and so on and so forth until eventually reaching this design line, which was still fairly far away from what the advanced detectors were going to do. Now, the expectation is that a lot of the gravitational waves we're going to be observing are below the sensitivity. They're buried in the noise. So we need to pull them out. So how do we pull them out? We do something we call a match filtering. So we create filters, models, for what we think the gravitational waves look like, okay? And once we have those models, we calculate a cross correlation between that data and the model. Cross correlation mathematically looks as follows. The curly L is the so-called likelihood function. And these brackets that appear here represent an inner product. Now, S and H correspond to the signal and the model. So I'm subtracting the signal from the model. So this is nothing but the inner product of noise with noise if the signal is composed or the data is composed of a gravitational wave plus noise. So the likelihood is nothing but e to the minus 1/2 n squared. So it's the noise model. Writing this like that assumes that noise or the properties of noise are Gaussian. Now, one can show that the best inner product for this type of matched filtering analysis is as follows. You're integrating the absolute magnitude of the Fourier transform of the signal minus the Fourier transform of the model, weighted by a spectral noise density curve that's essentially a measure of the noise in the instrument. And the model, this H that appears here, is obviously a function of frequency because of the Fourier transform of the response of the instrument to an impinging gravitational wave, but also depends on a vector of parameters that characterize the system that generated the gravitational wave. So those parameters are things like the masses, the spins, the distance to the source, and so on and so forth. So the game here is to compute this over and over and over and over again for different values of lambda until one finds a set of lambdas that minimizes that inner product or maximizes the likelihood. Okay. Of course, you have to vary a very high, well, this vector here can be 15-dimensional or 20-dimensional, depending on how complicated the model is. And that means that one has to use sophisticated methods to sample this parameter space, because if you just grid in a 15-dimensional space, you would need to have, many billions and billions and billions of evaluations to have a dense enough exploration of that space. So instead of doing that, what we do is something, for example, called Markov chain Monte Carlo explorations, where we select a point in parameter space, we evaluate the likelihood there, and then we jump to another point and we evaluate it there, and then we have ways to decide whether we accept that jump or not, and then we continue jumping in a Markovian way across this parameter space. So what I'm showing you here, it's a reduced corner plot where you've done we're going to do a Markov chain exploration of parameter space. I'm just going to show you 2 dimensions. So I'm going to show you distance, and I'm going to show you mass. Okay, and so this is the value of mass and distance that we have injected. So we've artificially selected a data that is produced by a binary with this mass and this distance. And we're going to try to see if we can find it with our template. So a point here corresponds to an attempt, a particular jump, at that point in parameter space. As I jump around this parameter space, I'm going to build a histogram of, the value of the likelihood at these points. So as you see, the changes are jumping around and jumping around this higher dimensional space, and you see this projection into this 2-dimensional plane. And as I do so, I build up a histogram of the probability that the data is well described by the model with this particular set of parameters. And that's essentially what you do in gravitational wave data analysis, except that you do it in 15 dimensions or 16 or whatever number of dimensions, depending on how many parameters you want to estimate in your system. Okay. Great. And so clearly, how much information we can extract from the signal depends very delicately on the model that we use to understand the signal and on how accurate that model is. So in order to understand binary systems, we need to then describe accurately how binary objects spiraling to each other collide and generate gravitational waves. And typically we do that by decomposing the inspiral or the coalescence into an inspiral phase where the objects are moving relatively slowly with respect to each other. Velocity is less than 0.3 the speed of light, roughly. And then a merger phase where the objects are sufficiently close to each other that they merge quickly, and there one has to solve the equations using numerical relativity techniques. And then a ring-down phase where the objects have merged and now into a remnant that now needs to relax into its final configuration by emitting quasi-normal modes, ring-down gravitational waves. And that part can also be modeled with numerical relativity or with black hole perturbation techniques. In the inspiral, we employ perturbative techniques like post-Newtonian theory for comparable masses or cell force theory for extreme mass ratio inspirals. Okay, and combining these different sets of approximations for comparable masses, we can construct hybrid waveforms that describe the full coalescence accurately, and hopefully accurately enough. Okay, so this is what we do in general relativity. How do we use then these models to extract information about fundamental physics? And so in order to answer that question, we got to talk about what is fundamental physics. And that depends strongly on who you ask. Okay? So if you ask an expert in nuclear physics, that person's going to tell you that what matters the most is to understand the equation of state and out of equilibrium phenomena inside of a neutron star where the temperatures are very low, below an MeV, and the densities are supranuclear, and you might have the confinement inside of the star and a quark gluon plasma, and we want to understand the properties of that and how that connects to the QGP that's detected in heavy ion collisions. If you ask a particle physicist, then that person is going to tell you that what really matters the most is understanding the particle interactions and the field interactions, and to understand how we can complete the standard model in a way that perhaps is consistent with gravity and so on and so forth. And if you ask a gravitational physicist, then they're going to care most probably about black holes and most probably about gravitational waves that those black holes emit, and whether there are any signatures of deviations from general relativity in this extreme regime where gravity is not just strongly nonlinear, but also dynamic. Okay, so in this particular talk, what I mean by fundamental physics is this last definition. Is the deviations from general relativity that we may be able to probe with gravitational waves, in the hopes that if we can detect something with confidence, then that might indicate a path toward understanding some problems that appear with anomalies we have observed and with theoretical issues we know exist in Einstein's theory of general relativity. Okay? Now, why would we want to probe fundamental physics with gravitational waves? After all, we know general relativity is right? You know, we've tested it for 100 years. We know from solar system observations and binary pulsar observations and cosmological observations, since you pass all tests with flying colors. And that's indeed the case. What I'm showing you here on the y-axis is a measure of curvature of a system. And on the x-axis, you see a measure of the gravitational strength or the potential of that particular system. So M is like a characteristic mass for the system, and it's like a characteristic separation. And what you see here are different observations that have been carried out to probe physics in this particular plane. So here on the lower left corner, you see this weak field test of general relativity, things like tests you can carry out with the LAGEO satellites, or with lunar laser ranging, or with perihelion precession of Mercury, and many others. They are weak field because they're weak potential, low curvature. Okay. As you move on, you see that we can begin to test general relativity with binary pulsar systems. And here's where the double binary pulsar systems would lie. And they are moving, they're getting us a little bit away from this weak field regime. Why? Because neutron stars are strongly gravitating nonlinear objects. But the orbital separation between a neutron star and a white dwarf, that's still fairly large. The orbital velocities that the systems experience are relatively small, like 10 to the minus 2 or so, the speed of light. With gravitational waves, we get access to this top right corner. And so here I am showing you the regime in this parameter space that the first couple of events that LIGO detected experienced. Okay, and what you see here is not a point, but a sequence of points, because during the observation, the potential that these systems felt, the interpotential, was changing because the orbital separation, the characteristic length, was changing. Okay, because the radiation reaction mattered during these observations. Pulsar timing arrays would be down here. And so from this point of view, these gravitational waves that I've been talking about, detected by any of these instruments I mentioned earlier, are probing this regime that I've called extreme gravity, where gravity is both strong and dynamic. Since up until now, we didn't have any data in this regime, this begs the question of whether there are deviations from Einstein's predictions that we had not seen before. So just because we've constrained this part, this lower left side of parameter space, that doesn't mean that automatically the top right corner would also satisfy Einstein's equations. And in fact, what some may argue that if you are going to see deviations from general relativity, you might expect them in this regime of extreme gravity. And so we should go ahead and do such explorations with the data. Problem, of course, is that there's a bit of a bestiary of modified theories of gravity of different degrees of completeness that one may wish to study. And there's so many that if you try to put a grad student to work on all of them, they might just not survive. So instead of that, let's take a page from the past and see what happened in the 1970s when there was also an outbreak of modified theories of gravity, okay? Fortunately, in the 70s, there were all of these solar system experiments that were coming online and that could allow us to place constraints on these theories. So the way that this was done in the 70s was to imagine that you had some data set from sample observations of the perihelion precession of Mercury, or for example, the Shapiro time delay experienced by light signals as they pass close to a strongly gravitated, well, to a body with with gravity, like the sun. So if you have a measurement of this, what you would like to do is compare it to something. So Ken Norvett at Montana State and Cliff Will, who was at Stanford at the time, well, actually he was at Caltech at the time and then at Stanford, developed this parameterized post-Newtonian framework. So what this framework did was to say, well, let's just think about ways in which we can parameterize deviations in the Shapiro time delay from what's predicted in general relativity. And they devised an entire formalism to figure out what the right number of linearly independent deviations could be. What they did is they parameterized the metric of a gravitating body in the solar system through certain post-Newtonian potentials. But let's not get that technical. Once they have a prediction for this generalized observable, which of course depends on, say, the distance of closest approach of the light ray to the sun and the distance between Earth and the source of the light. It also depends on some additional parameters that control the deviations away from general relativity, these gammas. So what they then suggested was, okay, what we should do is we should compare the data to this model and then place a constraint on this gamma, on this generic parameter. So doing this, you can think of this as placing a generic model-independent constraint on general relativity. But the richness in this is that once you have a constraint on this gamma parameter, you can, in principle, map those constraints to constraints on any one of these theories. All you have to do is go to these theories and calculate what gamma is for any one of these theories, which you can do by solving for a solar system metric in those theories. So in this particular case, for example, if you map to Brans-Dicke theory, you find that a constraint on gamma of 10 to the minus 5, which was observed with the latest most accurate observations of Shapiro time delay by a probe that's near Jupiter. Doesn't really matter, but it's a very good constraint on deviations from GR. That can be mapped to a constraint on the Brans-Dicke coupling parameter that is very strong. So for historical reasons in this theory, when omega Brans-Dicke goes to infinity, you recover GR. So a constraint of omega larger than 40,000 is very good. And you can repeat this for all the other theories and get similar constraints. So you can try to do the same now that we have gravitational waves and we have a different outbreak of modified gravity theories, if you want. And so one possibility to do this is to imagine that the data in this case is H plus and H cross, the plus and cross polarizations of gravitational waves that you detect at the instrument, at LIGO, for example. And what you want to do is you want to compare that not to just a particular H plus and H cross in GR or in any one of these theories, but instead construct an H plus and H cross that exists beyond any one of these theories. It's like a meta theory. So it depends, of course, on the masses of the systems, the spins, and all of the other parameters, as well as on some new parameters that control deviations away from the predictions of general relativity. And so what you then do is instead of comparing the GR model to the data, you compare this parameterized post-Einsteinian model or parameterized post-Newtonian model to the data so that you can place constraints on all of these parameters, including beta. Doing so allows you to place a particular constraint on beta. You can say beta is smaller than some number, and then that becomes a model independent, or more or less model independent, constraint on deviations from general relativity. What's powerful is not this particular constraint alone, but also the map that you can do between the constraint on beta and the constraint on the coupling constants of these theories. So you can go and you can calculate what H plus and H cross is in any one of these theories, so that you can get the constraint on beta, and then without having to do any data analysis, you can just look at the constraint on beta that was computed in general, and then map that constraint to a constraint of any of your coupling constants. And this was done, for example, for scalar Gauss-Bonnet theory, which I'll describe later, allowing us to place a constraint of roughly horizon size with the LIGO data. That's the general idea of the PPE formalism. And of course, the question is, how do you go about constructing a general deformation of general relativity for the gravitational waves emitted by binary systems? Well, so you can look at specific theories of gravity, and people have done that, including myself. And just within that theory, you have an action, and you can just go and calculate everything. Another approach is to say, well, let's consider the pillars of general relativity, and let's begin to add interactions to the Einstein-Hilbert-Lagrangian that break some of these pillars, or in a sort of effective field theory type approach. And you can then ask whether interactions of this type map to specific modified theories of gravity, which in this case occurs. And you can then, with this general action, calculate the gravitational waves that are predicted by this sort of meta theory. And because you can map the action to the action of any one of these theories, you can then map the H plus and H cross you calculate from this meta theory to the H plus and H cross of any one of these theories. That's another way to do the calculation. So this has been done in a variety of ways. So in spiral regime for comparable mass systems, you can do this by parametrically deforming the Hamiltonian and the radiation reaction force, which in spiral you can represent through a power of the velocity. So alpha h here is a constant that tells you how far away from GR you are, whereas velocity is the orbital velocity, and a is a number that tells you what type of deviation you're considering. And you can do something similar with a radiation reaction force. You can deform the waveform generation, allowing for additional polarizations of your tensor gravitational field. There can be up to 6. And you can even modify the way that tensor perturbations propagate, because the propagation speeds may not be equal to the speed of light. And so you can do that also parametrically. Putting all of that together, constructing your gravitational wave, you can show you effectively get something like this, where you get an amplitude modification that depends on a constant alpha that you want to constrain times f to some power a, and a phase modification that depends on beta, which is a quantity you want to constrain, times f to the power b, where b is another number. So a and b tell you what type of deformation or deviation from general relativity you're trying to constrain, whereas alpha and beta tell you how far away from general relativity you are. You can take waveforms of that type, and you can compare them to the predictions of modified gravity theories, and this has been done for a plethora of theories, allowing you to construct a dictionary between these PP waveforms and the predictions of those theories. With that dictionary, and tons of people have worked on this. It's hard to mention them all. With that, you can then place constraints, for example, on beta from the data. So what I am showing you here is going to be constraints on beta for different choices of this b. So you fix b to some number, and then you compare to the data, and you see what the posterior on beta is from the data, and therefore what the constraint on beta is. And so you can place constraints on anomalous accelerations of a binary system, on the existence of scalar dipole radiation, on possible Lorentz violation in the gravitational sector, on parity violation, and so on and so forth. Okay. And the constraints look more or less like this. So these are exclusion plots. Everything below these lines is ruled out. And the reason you see different lines is because the blue line, the blue dotted line, is a projection that was made in 2011 before there was any data, whereas the green, red, and purple lines come from looking at data itself. Okay, and so one thing you notice is that the predictions from 2011 were actually pretty spot on, which makes me happy. But also, what you see is that the different data sets are constraining, are producing consistent constraints in this parameter space, ruling everything out below those lines. Everything we have observed so far seems to be consistent with general relativity. Here are more updated constraints when you include even more data sets and when you combine them. So when you choose different values of B, you can place different constraints on essentially beta. This is another way of parameterizing the deviations. And this is this plot comes from one of the many LIGO papers. Okay. But then we're not done there. We can actually we can map those constraints on beta for a given value of B to constraints on specific theories. So let's do that for scalar Gauss-Bonnet gravity. So scalar Gauss-Bonnet gravity is a theory where there's an additional scalar field that couples to the Gauss-Bonnet curvature invariant. So the action is the Einstein-Hilbert action plus a dynamical term for the scalar field plus a non-minimal coupling of the form phi times Gauss-Bonnet. A theory like that allows for the existence of black holes, but the black holes are different from the black holes of general relativity. Why? Because each black hole in a binary will be endowed with a scalar field that has a monopolar type structure, almost as if the black hole had a scalar field, an electric field, even though there is no electric field, there's just a scalar field. Now, you know from electrodynamics that if you have two little monopoles moving around each other in a circle, that emits dipole radiation, electromagnetic dipole radiation. Well, the same thing happens here. If you have two black holes with a monopolar scalar profile, as the black holes move around each other, they will emit dipole gravitational radiation. That dipole radiation will accelerate the in-spiral relative to what's predicted in general relativity, therefore modifying the phase and frequency evolution of the gravitational waves, which then imprint onto the gravitational waves you predict. You can compare that model to the data. Again, it maps to a particular B in the PP scheme. You see that that's not present in data, which then allows you to place a constraint on the coupling constants of this theory using post-Newtonian theory. So what you see here is one such marginalized posterior distribution for the square root of the coupling constant. And you see that to 90% confidence, this particular event, GW 190728, is telling us that for the model, the scalar Gauss-Bonnet model, to be consistent with the data, given noise fluctuations in the data, then square root of G of alpha has to be less than roughly 7 kilometers. Okay, and you can repeat this for different observables. Okay, and you can even combine them all. Okay, all observations we have made seem to be consistent with general relativity. Each of them give you a different posterior, marginalized posterior, and you combine them all and you obtain a bound on square root of alpha of roughly 1.7 kilometers, which was the first constraint on scalar Gauss-Bonnet gravity with gravitational waves, and much more stringent by like 8 orders of magnitude than any other constraint we had until that time on this particular theory of gravity. Okay, so let's now move on then into what we can do next with gravitational waves. Okay. Now, one way to understand this PP formalism is as follows. Imagine the space of all possible theories of gravity. Okay. Now, GR is going to be a point in that space. And imagine that point is equipped with all of the properties of general relativity, as well as the predictions for gravitational wave emission of a binary system. Now, if you have a modified theory of gravity, that modified theory of gravity will be represented by a different point in this space. Let's say Brans-Dicke theory might be there, and then the distance between Brans-Dicke theory and GR in this space will be controlled by the value of some coupling constant in that theory. When the coupling constant, if the theory has a smooth limit to GR, when the coupling constant goes to 0, then this separation goes to 0, and the Brans-Dicke point becomes very close to the GR point. You can now do the same for other theories of gravity, like a massive graviton dispersion relation or a massive graviton theory. And similarly, that theory will have a coupling constant, maybe like what the mass of the graviton is, such that when the mass of the graviton goes to 0, then the massive graviton point in this space goes to the GR point. So far, so good? Okay. Now I can repeat this with a bunch of different theories. Before doing so, let me just indicate the direction in which I'm deviating from GR when I consider Brans-Dicke type deviations with a vector, and that when I consider massive graviton deviations with another vector. Okay, so how far away I am from the point GR tells me the magnitude of the deviation. So let me compactify that space so that everything that is on the perimeter of the circle is infinitely away from general relativity. Okay, that's just a compactification. And now I can drop in this space other points that represent other modifications to general relativity, right? And some of them might lie on top of the Brans-Dicke line because they might produce deviations from general relativity that are similar in the inspiral from those predicted by Brans-Dicke. But other points will be somewhere else in the parameter space. But for each of those, I can classify them in a post-Newtonian approximation by looking at the leading order deviation that they introduce, just a classification. Of course, they introduce deviations at all post-Newtonian orders, but they will uniquely start at some post-Newtonian order, some power of V over C. So I can have -1 PN deviations, 1 PN deviations, and so on and so forth. I can go in the positive PN direction. I can go in the negative PN direction. So when I observe a gravitational wave, because the observation is not perfect, there's statistical noise in your detector, what I'm asking is, how consistent is that data with GR in some sense? So how far away from GR am I allowed to go due to the noise fluctuations in my data? So what I am doing is I'm placing a constraint in this parameter space, some shape, okay? And so that's the essence of the parameterized post-Einsteinian frame. Can we go beyond this parameterized post-Einsteinian deviation? This is not perfect. Not all theories of gravity allow you to do a classification like this because not all of them admit a post-Newtonian expansion in the inspiral. For example, if you have a sudden activation of a scalar field or a vector field in the inspiral, like spontaneous or dynamical scalarization or vectorization, that will turn on a very short time scale that is not related to the orbital time scale and it's not necessarily related to the radiation reaction time scale. And that sudden activation cannot be represented with a polynomial velocity. It's more like a theta function activation of a new degree of freedom. And there are other examples like that. So one way to go beyond is to use AI. So how do we use AI? We, in very, very basic principles, because that's how much I know about AI, is you start with something you understand and you train your machine on what you understand. And you do so in a way to allow the machine to have enough flexibility to also extract from a data set, not just what you trained on, but also things that maybe you didn't train on to some degree. Of course, if the data is very different from what you trained on, then you're going to have a problem. But if it is in between the gaps of what you trained on, it might be okay. So we call this approach a neural post-Einsteinian framework or parameterized post-Newtonian framework. The general idea is to construct a training set from your GR models, okay, as well as from your non-GR models, and to encode that training set into some set of parameters, of reduced parameters, such that when you decode that reduced set, you can reproduce what you trained, as well as other things you didn't train on. Once you've developed a machine like this, you can then deploy the machine onto the data and let the machine figure out whether what you've detected in the data is consistent with a polynomial, like what I've put into the PPE formalism, or maybe not. Maybe it's consistent with something else that is not a polynomial in velocity in the spiral. That's the general idea, to detect not just leading order deviations, but also higher PN order deviations, to detect untrained higher PN order deviations, and to detect untrained non-polynomial deviations of general relativity. That would be the dream. So we have been working on that for more years than I care to admit at this point. And the latest incarnation looks more or less like this. Here are our encoding parameters Z2 and Z1, where we've trained on GR in the spiral, as well as a bunch of different theories of gravity. And you see here the directions that I was showing you before in my little cartoon. Okay. And here you see where different modifications to GR would lie. So if you put in a scalar Gauss-Bonnet or EDGB modification at leading order, would lie on this -1 PN line. Whereas if you put an EDGB or scalar Gauss-Bonnet modification with not just the leading post-Newtonian order term, but the higher PN corrections as well, then it actually doesn't lie on the line, but it lies close to the line. So what the the NPE can do is it can place constraints everywhere on this circle and not just along a given line. The traditional PPE test is you fix the angle here and you say, how far away from the origin does my data allow me to go? And then you have to pick another angle and do it again. And then you have to pick another angle and you have to do it again. With NPE, you don't pick an angle. The machine just constrains an entire region, period. And so here are some constraints that you can find by deploying the machine on data. And what you first find is if the data that this is synthetic data, this is not real data. So we inject it, for example, as a GR signal. And then we ask, we injected a non-GR signal, a scalar Gauss-Bonnet thing. And then we ask, can we recover that scalar Gauss-Bonnet injection? And we can do it with the standard PPE, and that's the posterior see here in green on the left, for the magnitude of C and for the argument of C. For the argument of C, there's no posterior because you fixed the argument of Z, the angle. You fix the angle when you do PPE. So you just constrain the magnitude. That's the green posterior here. And then the other two posteriors, the blue one and the orange one, show you how the NPE can constrain the magnitude of Z and the angle of Z to very similar accuracy without having to fix what the argument of C is, without fixing the angle. So you can recover not just that there was a deviation, but what type of deviation there was. So I don't know if I'm running long or short, but actually I think I'm good. So what have I told you so far? So I've told you that gravitational waves are beginning to probe this extreme gravity regime. They're beginning to place constraints on this fundamental physics that I described before. Okay, this is the beginning because there's many more data sets that are coming, and we need to be able to be prepared to analyze all of them and allow ourselves to be surprised. There will be specifically detectors with higher sensitivity coming online soon. And this will not just lead to many more detections that we have now, but they will also give us some events with very high signal-to-noise ratios. Those events you can use to learn about things that we have not yet learned. So things like screening mechanisms that might be present and I have not really discussed. You could also ask whether there is new physics in specific new sources that we have not detected with ground-based instruments. Extreme mass ratio in spirals, for example, cannot be observed by ground-based detectors because the frequencies of those gravitational waves are below 1 hertz. So you have to go to space. So it is possible that we may be able to place stronger constraints than what we have already placed using these Embry gravitational waves, searching for scalar dipoles present in those in the small objects. And of course, we can continue to look at agnostic tests that perhaps employ some of these neural network ideas that I described earlier, as well as new tests on the polarization content of the gravitational waves and the speed of gravitational waves. So I think the future is very loud and it's going to be very interesting. So please stay tuned. And I'll stop here. Thank you.
For the wonderful talk. Any questions?
Okay. You talked up. You maybe maybe yeah. You focused on the modified gravity theories. But if you let's suppose that we detected some signal which is not expected on one. Then if you want to say that is actually effect of modified gravity, then you have to rule out the possibility of the environmental standard matter field effect, standard field which minimally coupled to gravity. So could you comment about that?
Yeah, absolutely. So that's a very good point. The systems that we observe are not necessarily clean or as clean as we wish them to be all the time. They may be inside of some sort of dark matter spike. They could be, the binaries could be surrounded by an accretion disk if you're considering supermassive black holes, and so on and so forth. So the question that you're asking is, how do we distinguish between things that are just perfectly good astrophysics from things that are deviations from general relativity? That's a very active, active research area. But I mean, I should also mention that that is not the only thing we should worry about. Even if there are no astrophysical environments, we might still get confused and think we've detected a deviation when in reality there isn't any. And our confusion just stems from the fact that our GR base model maybe is not accurate enough to describe the system that we have observed. Maybe the system had, some eccentricity and we didn't include eccentricity. Maybe the system had some strong spin precession and maybe we did a test without allowing for spin precession. And so those mismodeling, so the astrophysical systematics and the mismodeling systematics have to be taken into consideration very carefully before you can make a statement. So astrophysical, so in order for you to be able to claim that you've detected a deviation from GR, then you would hope that you've detected consistent deviations across many, many different events. Because an astrophysical environment situation might occur, for example, microlancing or millilancing might occur for a particular source. Here, what I mean by millilancing is that maybe there are some sort of black hole in between the source of the gravitational waves and us. So as the wave comes through, then there's bending of the gravitational wavefronts, and there can be essentially an echo of the signal, and that echo might occur superposed with a primary carrier, and then you get interference between the two that might get confused with a GR deviation. It should be very specific, right? But that will happen for a particular source where there happens to be a black hole in between the source and us, which is very unlikely. And having that occur for yet another source and yet another source and yet another source becomes like unlikely to the infinity, right? And so at some point, you just don't expect that to be true unless everything we observe happens to have a black hole right between us and the source. And so those deviations are not going to be correlated across sources. But deviations from general relativity, if they are there, they should be there for depending on the theory of gravity you're considering, but there, for some of these theories, there's expected to be there for all the sources of gravitational waves from black holes, say in a given mass range. And so by looking for those coincidences, you can begin to separate things. Another way to separate things is to ask, what kind of deviation from general relativity would I extract if I have an astrophysical effect, or if I have a mismodeling effect, but I am still in GR? What am I biased toward? Does the data begin to support a deviation from GR that looks like, I don't know, like a dipole or like an anomalous acceleration? Or does it look more like something else that appears at higher post-Newtonian order first? And if there's a clean separation of those effects, then any deviation that could be mimicked by an astrophysical event or by an astrophysical environment, you would just, quote, or you would take with a grain of salt, if that makes sense. Thank you.
There is a question from the online participant. Kazuyuki-san, please ask.
Hello, can you hear me?
Yes.
Okay, so you mentioned that the modeling for the gravitational waves is done in 3 parts, right? Like the in-spiral and the merger and the, I forgot the term. But how do you define the transition point? For example, the transition point between the merger and the in-spiral?
Yeah, that's a good question. So this is a colloquium style talk, and I'm oversimplifying things a little bit here. So whether you split things into an in-spiral, merger, or ring down depends on the mass ratio of the system that you're considering. But for comparable mass systems, you can do so. And what you do is you compare your post-Newtonian approximation to your signal to numerical relativity simulations. And so you try to start your numerical relativity simulations as early as possible, and you try to push your post-Newtonian approximations as late as possible to try to find a buffer zone, a regime where both approximations are simultaneously valid. And so to extend the validity of the post-Newtonian approximation, you can attempt to implement some resummation techniques where perhaps you work with a resummed Hamiltonian, and you resum the radiation reaction force in some particular way, and then you solve the radiation reaction enhanced Hamilton equations, and that leads to the so-called effective one-body approach. And you hope that that approach is more accurate than just a plain Taylor expansion. And you compare that to numerical relativity simulations that start as early as possible. And then you glue them in a regime where both of them are valid. And that's one approach. I think nowadays that transition, can also be shrunk significantly with advances in effective one-body techniques, so that you can effectively just do the whole thing with a numerical relativity calibrated effective one-body model, and then just glue that to a ring-down type signal. But either way, what you end up doing is comparing these numerical relativity simulations to the post-Newtonian calculations to try to hybridize them in some specific way.
Thank you.
Yeah, I'm interested in the use of AI to go beyond the parameterized post Einstein. So your strategy seems to introduce a functional degree of freedom to model the waveform. I mean, so yeah, in the PP formalism, the frequency evolution, the phase evolution is modeled by the polynomial. Use of AI introduce a functional degree freedom, or the not functional, but for me it seems we cannot it's not inevitable to introduce a large number of parameters. So
right. So this is that's a good question. So just repeat the question, right? So in the parameter post-Newtonian model, you are asserting that the deviation from general relativity can be represented as a polynomial in velocity. In the AI technique that I described, which is just to throw in technical terms, it's called a variational autoencoder. We don't have to introduce a polynomial representation of the deviation. That's the whole point. You just train the VAE on as many modified signals as you can possibly get your hands on, including those that do not have a polynomial representation.
Train with not only polynomial.
You don't, so it's not a fit, right? So the VAE is not that you just construct a model that's some other polynomial and you fit it to your training set. It's much more complicated than that. There's a penalty function that you have to minimize, but you never end up having to like put in a particular functional form for like the phase correction, for example, like you do in post-Newtonian. And so it allows for deviations that are in principle non-polynomial without you having to specify a basis function. I can show you the mathematical details later if you want.
How, yeah, it seems that the one with model is a way to model the waveform.
To model the waveform.
Yeah, you use a VAE to model
To model the deformation from GR.
GR.
That's right.
And is it characterized by the many parameters?
No, so we only introduced two parameters in the encoding set, and those parameters are not like a polynomial in velocity or anything like that.
You mean the hidden rate, hidden variable
Yeah,
has only a small number, two
Yes,
or
that's
three parameters, and it characterizes the modification of the waveform.
That's right. So your training set is essentially many different frequency series. So it's like delta phi as a function of f, or delta phi can be many different functions of f, not all necessarily polynomial. And that's like your training set. And then you encode that into a hidden set variable of 2. It's getting pretty technical. Let's continue this later.
Yeah. What I concerned was that if we introduce many parameters, then when we carry out much filtering, it's quite difficult. So
yeah, that would be hugely problematic. And you can feed a horse with enough parameters. There's only 2 that we've introduced so far.
Yeah.
But I mean, it's just the beginning, right? Like we've trained on signals coming from binaries that are not spinning for now, right? Like because you got to start somewhere. And we only considered GR waveforms as well as waveforms for like 6 or 7 different modified gravity theories, with like 2 of those not having a polynomial representation. So it is possible that as you consider more complicated binary geometries, like with spin precession, and as you consider more modified theories of gravity in your training set, that you may need more parameters than the 2 that we have introduced. And so that remains to be seen.
Any other questions? Or you can ask questions from online.
Yeah, I have a question. So on this slide, you're writing stacking.
Stacking.
Yeah.
Yeah.
So what kind of thing are you thinking about?
Well, so I wanted to make reference to some of the work that other people have done on stacking. It's not particularly my work, but the general idea here is that if you have a if you are trying to constrain coupling constant in a particular modified theory of gravity, then that constant, if it's not 0, it will be the same for all binary black holes that you're detecting. And when that is the case, your posterior on, say, for example, that coupling constant from one event can be combined with the posterior from another event, and so on and so forth. And if all events have the same signal to noise ratio, the constraint on the stacked data set, which you're essentially multiplying all of the likelihoods together, just becomes roughly square root of n stronger than the constraints
So you,
from a single
you
event.
have done for the EDGB case.
Yeah.
Yeah.
I haven't actually. Kento Yagi
Yeah.
did. Yes, you know him. Now, if you're trying to do this with model independent tests, when you're constraining, say, beta, then it's much more difficult and you have to be a lot more careful because that beta that I wrote down in these slides, in principle, depends on the masses and the spins of the objects. And those objects are all different in the catalog. And so you cannot, in principle, stack beta. What you need to do is you need to constrain beta, then map that to a particular theory where you have your particular coupling constant that all the events share, and then stack that.
And maybe at that point we also have to introduce the power of AI. There might be various various way of stacking.
Yeah. And some people have actually been pushing this stacking idea a little bit further by doing something called hierarchical modeling, right? Where you just say, well, beta is not the same across all sources, but it depends on the masses through some population model that I'm going to prescribe. And then if I say that beta depends on the masses with some population model, then I can try to constrain the properties of that population. This is similar to when people use the different observations of the masses of the different black holes in the catalog to infer the mass distribution or the spin distribution. And so that's another approach that people have been making or studying. I'm just a little bit concerned about whether those population models for these parameters are good enough to tell us anything useful. But yeah.
Regarding neural PP, I'd like to confirm go back the NPP.
So NPP.
Injection studies. Yeah.
Sorry. This can be fixed easily. Which slide? This one?
Injection studies. Yeah, this one.
This one. Oh, this one.
Yeah, just 30. This one. Yes.
Mhm.
Okay, yeah. I'm wondering. Yeah. First, I want to confirm this is a PP injection case, PP signal.
Well, so there's two injections here. I didn't know how much time I had, so I went a little bit fast here. So there's two injections that are represented by the blue dashed line vertical and the orange line. So the blue line corresponds to a scalar Gauss-Bonnet injection with just the leading order deviation calculated by many of us a long time ago.
Parameterized by PP.
It's perfectly parameterized by PP. And the orange line corresponds to an injection that includes not just the leading order, but all of the subleading orders that have been calculated by a bunch of people. That's what the orange one is. And given those injections, you can then try to recover with a PPE model or with a VIE model. If you try to recover with a PPE model, just a single PPE parameter like we always do, then you get the green posterior here. When you analyze the injection that has the next to leading order terms. So I'm not showing here the recovery when you inject with just the leading order term for the PP. Okay, so that's what this thing is. And there's no posterior for the argument of Z because in PPE you assume the angle. You always pick a particular PN order, right? The other two, the blue one and the orange one, correspond to what you get when you analyze the leading order injection or the next to leading order injection, both with a VIE. So you see here that the posteriors, the orange and the blue one and the green one, they're all consistent with each other. You're getting more or less roughly the same constraint. But when you do it with a VAE, you can also identify what type of deviation from GR was dominantly present, which in this case is a -1 p.m. correction because it's a scalar Gaussian event for binary black holes. I see you're still confused, so continue asking. That's okay.
I'm confused. Yeah, left panel. Yeah,
Left.
injection is orange one case. Orange injection case. Posterior is.
Oh, you're concerned that this orange line doesn't lie on top of this over here
Yeah. What? Yeah.
because there's because there's noise. There's a noise realization that has shifted. This is not a zero noise injection. I mean, if I did it for a different noise injection, it would shift in a different direction. Also, this is all super preliminary and nothing has been published yet. So don't go stealing my ideas. I know who you are.
No more questions from online. Okay. Any more questions? If not, let's close this colloquium. So let's thank the speaker again. Thank you so much.